Chemistry 1124. We're going to talk about pages 17 through 21. Oh my goodness. Wow, they cover a lot of territory in these few pages. And some other chemistry textbooks that I have used take some of this information and spread it out over a period of about 50 pages, 3 modules, 3 chapters, and they cover it in 3 pages in here, and even throw in some things that most high school books don't even cover. So a lot of detail. Some of it you can just skip. They're throwing it in just to make it look like, wow, we're really doing something complicated, which you are. And then some of it is things you need to know. Some of it they just barely touch on and don't explain very well. So this video may be a little longer than a normal, 5 to 10 minute video, because I just want to kind of speak your way through it, okay? Talk you through some of the stuff that you're going to hit on these pages. I will give you a tip right here at the very beginning that if you look back at your physical science paces, maybe your supervisor, teacher has some of the physical science paces, the first 6 cover chemistry, and you'll find some of the content covered in there that they assume you already remember and you're just reviewing here in chemistry. But if it's brand new to you here, you might read it in the physical science paces and see if that makes a little more sense, and kind of put the two together to kind of get your understanding. All right, but let's dive in and see what we can explain here. Atoms bond together, okay, to form different compounds. So for instance, sodium and chlorine, sodium chloride, is table salt, right? Well, we're going to cover that actually later, and that is an ionic compound. And in an ionic compound, one atom is a metal, and it is so willing to give up an electron. It just is. If any other atom comes near it and says, I want your electron, it says, sure, you can have my 1 or 2 electrons in my outer shell, my valence electrons, because that means the shell underneath is full octet, and they're happy, okay? That's the goal. All atoms want to have 8 electrons in their outer shell, and then they are happy. Sorry about that. So, meanwhile, we have the nonmetals. Those are, let me grab my periodic table here. If you look at your periodic table, the metals are over here, okay? The nonmetals are in this upper right-hand corner, and then we have the metalloids going across this heavy line, jagged line here. That's the metalloids. So if you take a nonmetal and you bond it with a metal, you have an ionic bond. Because the nonmetals already have 6 or 7 electrons, they just need 1. And the metals want to get rid of 1. So that makes it real easy. But by totally giving up or totally gaining an electron, they become electrically charged, positive and negative charge, and the opposites attract. All right, so that's later. Right now we want to focus on, and then later they're going to talk about metallic bonds. That's bonding between metals. The main thing we're focusing on here is what's called covalent. Let's think about what that word means. Co means sharing, together, right? Cooperation. The word valent comes from the root word valence, the valence electrons. The valence electrons are in that outer shell, and so they are sharing electrons in the outer shell. And when I think of this, I forget where I got this picture. I think it's in one of the paces. Here, for instance, chlorine, and here's hydrogen, and they have some electrons between them that they want to share, and so they are both like teenagers fighting over a basketball, and they're both holding on. They're not going to give up until the referee, calls it and says it's a jump ball, in basketball. Well, here they're going to hold on for dear life, and they are stuck to each other because there's no referee to separate them. So that's what a covalent bond looks like. I'll come back to the polar and nonpolar in a minute. I want to point out though that it's only nonmetals. No metals, only nonmetals that form the covalent, and they are sharing. Keyword covalent sharing, okay? Now you might be a little confused, students often are, because up here is hydrogen and it looks like hydrogen is listed as a metal. Technically, it acts like a metal because it only has one electron and it's willing to give it up. However, it is a non-metal. It's a gas. So it really is part of this non-metal family, okay? So let's take an atom like water, H2O. Oxygen is in family 6. And if you look at the periodic table and look at the electron configuration on here, you'll see that in the second energy level, 2s2, 2p4, that means it has 6 electrons in the outer shell. Each hydrogen has 1 electron. Hydrogen wants to have 2 to be happy. Oxygen has 6 and wants a 7th and an 8th, and then it'll be happy. So, show you a little picture here, a little diagram. So we have oxygen, and it has 1, 2, 3, 4, and then a 5th here and a 6th electron there. Hydrogen comes up and says, hey, share one of your electrons with me, I'll share one of mine with you, and we'll have a pair of shared electrons right here. And this other hydrogen comes up and says, hey, I'll do the same thing over here. You have 1 electron you can share with me, I have 1 electron to share with you. So they share. Now, oxygen thinks it has 8 because it's sharing 2. Hydrogen had 1, but now it thinks it's sharing 1 of these electrons from oxygen, so it thinks it has 2. That's all hydrogen needs to be happy is 2. And so we have a molecule. Okay? So they're like holding on to shared electrons, and that's what bonds them together. So that is a covalent bond. Let me come back to the polar nonpolar again in a minute. Let me talk about CH4. Carbon is in family 4, which means it has 4 electrons in the outer shell. So it has 4 unbonded electrons. So each of these 4 sites on carbon is able to bond with another atom. So if a hydrogen comes up on this side, and one comes on this side, and one here, and one here, each of these 4 hydrogens is sharing 1 of carbons and sharing 1 of its own with carbon. So each hydrogen thinks it has 2 and is therefore happy. Carbon already had 4, but now it's sharing 1, 2, 3, 4 more, so now it has 8 electrons, and so it's happy. That's the goal. We want all of our atoms to be happy, and a full octet is how they're happy. Okay, full outer shell of electrons. So this would be CH4. Can I leave that up here? Will it stay? Ah! All right. What do I have next? Well, let me do NH3. Okay? Nitrogen is in family 5. So it has 5 electrons in its outer shell. I'm going to let this blue one represent nitrogen. With 5, that means it has 2 electrons that are using up this 4th site right here. Okay, so 2 electrons that it can't share. But then these 1, 2, 3 sites have 1 electron each that they can share. So we have 1, 2, 3, 4, 5 electrons. Again, a hydrogen coming up and saying, hey, can I bond with you? I'll share one of mine with you. You share that one with me. We do that on 3 sides, 3 sites, and we have NH3. Okay, so that's what it would look like. And then the last one, your PACE already talks about double bonds. Woo! So oxygen has 6, which means it only needs 2 more to be happy. Meanwhile, carbon, as we mentioned, has 4 electrons. It wants 4, and it has 4 that it can share. Well, look, here's what happens. Carbon is in the middle with the 4. Here comes an oxygen and says, I'll make a double deal with you. If you share 2 of your electrons with me, and I'll share the 2 that I have available. I'm sorry, this is oxygen. So it has 1, 2, 3, 4, and then here's a 5th and a 6th. It says, I'll share my 5th and 6th electrons with you, carbon, if you'll share both of your electrons with me. Another height oxygen comes up on this side, says the same thing. Let's share 2 and 2. So now we have carbon dioxide, carbon with 2 oxygens, carbon dioxide, and it forms these double bonds. Okay? Now let's talk about what polar and nonpolar means. Just like a battery has a north pole, a negative pole and a positive pole, or a magnet has a north pole and a south pole, we talk about atoms having a positive zone and a slightly negative zone. No, not totally positive. So this little symbol, and they have it in your pace, and I don't know if they say what it is. It's the Greek letter delta, which means just a very little bit, okay? Delta positive means slightly positive. Delta negative means slightly negative. Now let's think about what that means. Just like in this picture, the chlorine in this case is trying to share electrons, but it is much bigger. So it's more like a bully. And it says, hey, compared to you, junior high guy, I can hold these electrons closer to me than you can. And the electrons spend more time flying around. In this case, I'm talking about hydrogen and oxygen to form water. So these electrons are being shared are actually spending more time around the oxygen than they are around the hydrogen. Okay? There's only one electron being shared. So sometimes the electron is being pulled in and whirling around the oxygen. Well, what happens to the hydrogen? It only had one electron. So if that electron is here, what's exposed is its nucleus with 1 proton. Okay? Protons are positive. So that means this zone is slightly positive. This zone is slightly positive. And then around this is slightly negative, because the electrons are spending more time around the oxygen than they are around the hydrogen. Does that make sense? Okay? So yes, they're being shared, but they're not being shared equally. So the pace goes into greater detail talking about that this would be a polar molecule. I think it even talks about polar and nonpolar bonds. The bond is actually the bond between the 2 atoms. And if they're not identical atoms, which they're not in this case, then the electron, even though it's being shared, is being pulled stronger towards the oxygen than the hydrogen. So it'd be slightly positive in this side of the bond, slightly negative on this side. The key is to remember the electrons are negatively charged, right? So this is an interesting one. Each of these bonds, okay, stick with me, the word bond is between 2 atoms. So the bond is polar because this in the middle, was this the CH4? Yeah, so the carbon is going to hold the electrons more closely, more tightly than the hydrogen. So the electrons are spending more time around carbon, less time around hydrogen, which means all 4 of these are slightly positive. And this is slightly negative in the middle. So in this bond itself, we would say slightly positive, slightly negative. However, for the molecule itself, for the whole molecule, the whole outer part of this molecule is identical, right? They're all hydrogens, and all of the electrons are being shared equally, from each one to the center here. So that's slightly positive on all the outsides here, but there's no part of this molecule that is more positive than the rest of the exterior parts of this molecule. Same happens here. This is called a linear molecule because these atoms are lined up in a straight line, linear. And so we have a slightly negative out here, I think it would be. Slightly negative out here, a little more positive in the middle. I think the oxygens, if I remember right, are pulling the electrons towards them. So the electrons are being shared, but spending a little more time around the oxygens than around the carbons. Now you say, Mr. Stringer, how do I know whether it's spending more time around oxygen or carbon? Well, if we look back on the chart, a couple pages back in our PACE, and it talks about these relative strengths of the atoms. Their electronegativities, that's like how strong they attract electrons compared to others. So if we compare two atoms, we can look at their numbers and see which one has the higher number. That's the one that is more like a bully, pulling the electrons toward it, resulting in a slightly negative zone around that atom. Okay? But again, even though the bonds here are polar, this molecule itself, the two ends have the same charge. They're equal, slightly negative, slightly negative. So we would say that this molecule is non-polar. Okay, are you confused yet? So when we talk about polar and non-polar, sometimes we're talking about the bonds, sometimes we're talking about the whole molecule. And the PACE uses this delta positive or delta negative to indicate where its slight charge would be located. Let's talk about the last thing here. I guess did I do an NH3? I think I showed you that, yeah. So if I have, there are about 8 different elements that in nature are always found as pairs, twins, okay? Fluorine is never found just by itself. It's always 2 fluorine atoms bonded together. Oxygen is never found in nature, just oxygen. It's always a 2 atoms bonded together. But because they are identical atoms and they're sharing the electrons identically, there is no polarity. There's no positive or negative zone to the molecule nor to the bond between them. So these would be truly non-polar, okay? Whereas in these covalent bonds, though some of the bonds are polar, once in a while we will notice that the molecule might actually be non-polar. Kind of confusing. Hopefully this little introduction will help you now as you read, go back and study through this section, answering questions. There's not a lot of problems to solve. I may make a video for the one problem where we have to create a molecule. We'll kind of walk through those steps. Okay?